Hello again, this is Professor Jim Caffey in Springfield, Missouri, coming to you today with Chapter 24 in the OpenStax Astronomy free textbook. Chapter 24 is on black holes and curved spacetime. Here is an artist's rendering of a stellar mass black hole. So this is a star that has collapsed and died, and it is on the order of a few times the mass of the sun, and it generates this kind of black hole. Here is Albert Einstein, of course. What do you weigh in an elevator? If you go up to the top floor, you feel that your feet are being pressed against the floor. And so your weight changes in that situation. Weight is a perceived force on you. And if you exert more gravity on you, then you will have more force on you as well. In free fall, two people can play catch jumping off these tree stumps. Of course, we have our astronauts on the space station. Space shuttle is retired now. We don't have a space shuttle. But we are working on other ways to get into space with SpaceX and Blue Origin. Some of this stuff gets really tricky, but here is a classic situation to describe a black hole and what happens to what we describe as the fabric of space-time itself. So if you imagine you have this rubber sheet, you stretch it over 4 posts there, you put a bowling ball into the middle of that sheet, you're going to see that curve down, and that's what the gravity well does to space and time. It bends it. So any mass in space will curve space proportionally to its mass. Even light coming on the side of the sun will be bent around the sun, and we can see that. And we actually have done this during total solar eclipses. Now, if you get sucked into a black hole, there is no escape. You cannot escape a black hole. Very mysterious. John Wheeler, the great physicist who did a lot of work on general relativity theory from Einstein, and he popularized the term of the black hole in the late 1960s. This is Carl Schwarzschild. He was a German scientist and the first to demonstrate mathematically that a black hole is possible and to determine the size of a non-rotating black hole event horizon. Well, what is an event horizon? So as you get near a black hole, the event horizon around it tells you if you go past that, you're not coming back. You will not escape the black hole's influence. So that is the event horizon. You can have a binary star system become a binary black hole. We can look at gravitational waves in space with this facility. And that's going to do it for this short chapter, chapter 24 on black holes. Thank you for joining me for 10-Minute Astronomy.